All right, so let's take a look at this example. We just talked about the difference between chi-squared test for homogeneity and for chi-squared test for independence or an association, whichever you prefer. Finger length. In this relationship, is there a relationship between gender and relative finger length? In chapter 1, I think, we looked at a sample of 452 U.S. high school students who had completed a survey. The two-way table shows the gender of each student and which finger was longer on their left hand, their index finger or their ring. So we're basically comparing the index to the ring finger. Some people said they're about the same. Some people said the ring was longer. Some people said the index was longer. Make a well-labeled bar graph and compare the distributions of females and males. Describe what you see and then run a test to verify your observations. So looking at this one here, it looks like guys have a large percentage of people who have a ring finger that's longer, and girls have less, and certainly maybe more that have a longer index finger. So it looks like there's a relationship. There's an association. All right, so that's what I observed here. Whatever. All right, so let's run the test. So first, before we set up our null and alternate hypothesis, we need to know what kind of test we're running. So the question is, how do we know if it's homogeneity or independence? If you look at the table, you are not going to be able to tell because they look exactly the same. I got two variables, whatever. You have to read the stem of the question. We looked at a sample of 452 kids. That indicates one sample, and if it's a single sample, your test is independence or an association. So the null is that finger length and gender are independent versus the alternate that finger length and gender are not independent. Or the null could be that there's an association between finger length and gender for, I really should have for all U.S. high school students. Again, gotta fix it, gotta update these notes, I'm sorry. All right, check the conditions. They didn't say the sample was random. That's a huge problem. It just says a sample of kids who completed a survey. They probably had some kind of online thing that people chose to respond to. So we really can't, this is a huge problem. This means we can't generalize to any population at all. You could even argue that everything we're doing after this is almost like a waste of time. But just for the sake of an example, let's continue on and do it, I guess. N equals 452 is less than 10% of all high school students, probably. Maybe. Well, if it's U.S. high school students, that's definitely. All expected counts are greater than or equal to 5. So I checked it off, but we have to find those expected counts. So let's put it in our calculator and run the test to see what the expected counts are. So I went to the button next to the 9. I selected what looks like the 3x3 matrix, and I put in a 3x2 matrix. I put in the observed counts. Let's store this as 000 for observed. Let's just run the test. The thing is, this is exactly the same calculator function as option 8 here. Exact same one as the chi-squared test for homogeneity. Still one input. Exact same output. Let's check our expected matrix. Bars. Expected matrix. Those are all much larger than 5, so the check passes. And we have to put it somewhere on our paper. In this case, I decided to put it right here in this little 2x2 or two-way table. Expected counts are all bigger than 5. Again, you have to have them on your paper somewhere. Test name, chi-squared test for independence. 2 degrees of freedom. I just wrote down the test statistic and p-value. P-value is small relative to alpha. You have to explicitly compare it to alpha. Reject the null. We have convincing evidence that finger length and gender are not independent. In other words, there is an association. However, major problems with no random sample, but what can you do? All right, that's it. Pretty much the same. All right, so this is a bit of an exercise to link together a chi-squared test for independence with a chi-squared test for homogeneity with a two-sample z-test. So let's do this example. A study of customers' attitudes towards secondhand stores interviewed separate random samples. So we got multiple samples of shoppers at two secondhand stores of the same chain in two different cities. They recorded the gender of the subject. See the table to the right. So is this a chi-squared test for homogeneity or independence? Well, we have separate samples, so this is a chi-squared test for homogeneity, not independence. Why? We took two samples. Independence is used for only a single sample. Okay? Find the test statistic, degrees of freedom, and p-value for the following hypotheses. There is no difference in the true gender distribution of shoppers at these stores, at the stores in these two cities, versus there is a difference in the gender distribution of shoppers at these cities. So basically, just write down these values. So let's just run the chi-squared test for homogeneity here. I always like to open up a new document so I don't have conflicting variables. Graphing our calculator page, hit button next to the 9. Now this is just a 2x2. And we have 38, 68, 203, and 150. It's too small for my fingers. Store that into OBS for observed. Let's just run the test. Menu, statistics, stat tests, two-way table, input your observed, 15.33. Degrees of freedom, 1. P-value, I want a little more accuracy here, so I'm going to come up and grab it, grab it, hit enter, 0.0000901. Okay, so we would reject. That's not the point I'm trying to make here. All right, so let's let P1 be the true population proportion of women shoppers at store 1. So we can see our sample proportion, but so P1 is the true proportion. And then P2 is the true proportion of women shoppers at store 2. Okay, so we could run a 2-sample z-test for the difference in proportions. Since there's only 2 populations, and since the categorical variable is binary, guy or girl, there's only 2 outcomes, I could just test to see if those proportions were different. And if those proportions are significantly different, then of course the guy proportions are as well. We can do this in this case because there's only 2 responses, not red, blue, green, yellow, or multiple responses. So let's hypothesize that the difference in proportions is 0 against the alternate that it's not 0. So let's just run this 2-sample test. If you remember how to do it, escape. Having problems here. What's going on? Okay. Menu, statistics, stat tests. This would be a 2-proportion z-test, if you recall. Don't pick these. These 4 are for means. These are for proportions. These are for counts. This is for next chapter. So 6. Successes. So let's go. I'm trying to see my table because I can never remember numbers. There were 38 successes. Success in this case is being a woman. No. That's how many guys there were. Success is being a woman. Versus 241. And the second one was 150 out of 218. And I want to run a two-way test, a two-sided test, a two-tailed test. Test statistic 3.916. Z equals 3.916. And the p-value 0.00009. Does that look familiar a little bit? Let's make sure it's exactly the same. Hit enter. 0.901. So it looks like it's about the same. Yeah, looks like they're the same. And then the second question I was going to ask is, does it look, what was that? Does it look like there's a relationship between these two test statistics? If you square this one, it's going to generate that one. There's a reason why we call this the chi-square test statistic. If you take, or chi-squared variable, if you take 3.916 squared, it gives you this value here. And that the reason that is because this is got 1 degree of freedom. Basically, a chi-squared curve is kind of like a normal curve squared. And when you have multiple degrees of freedom, it's kind of like the sum of, let's say, 3 z-curves squared, kind of. Okay. So we only have this option when we have this type of situation. Okay. Two populations and a binary categorical variable. The thing that's nice about the chi-squared test is we could have 7 cities, and this variable could have many outputs. We could have 10 cities, and we could be studying, white, black people, Hispanic people. You could test different gender. There could be multiple outcomes in the response variable. A two-sampled z-test for proportions can't do that. This actually can do something that the chi-squared can't do. If we wanted to, we could test to see if P1 is greater than P2. This test gives us the opportunity to do a one-tailed test and see if one's greater. For chi-squared, you can just see if there's a difference and you can't put a direction to that difference. So each test has kind of got its pros and cons. And if you want to read this, that's pretty much what I just kind of said. So, all right. Last example. Next video.